Hello.
Organizer, Asha madam.
Yes, ma'am.
Yeah.
Shall we start, ma'am?
Gunjan join. Hello,
Yes, I can
Gunjan.
Yes,
see.
ma'am. Yes, ma'am, I joined.
So your camera is working.
Some issue with camera actually, ma'am. Sorry for that. I'm trying to resolve that only. But
At least starting time we can take the photo, and you rest of your talk you can.
no, that is not a problem. I can keep full time on. It's not an issue, but there is some issue with our college system today, so camera is not working.
From mobile you can join, so that just for the sake of the camera.
Okay, ma'am. Just give me 1 minute.
Asha madam, in the group you have written everywhere to join. The speaker has joined, so all of you join quickly.
Yes, ma'am.
Asha,
Posted. Yeah, yeah.
and
Posted in the
in
group, ma'am.
TOC group also you post.
Okay.
For mobile, then slide sharing, I have to see because I have uploaded everything on this system, my slides and all to share.
Slide and all you just to go through the system, and for your face camera you can put, so we can see one or two photo we will take.
Yeah, ma'am. Just 1 minute.
Now I can see you.
Now I can see you. Now I can see you. Now I can see you. Now I can see you.
So what you do, you speaker off. Gunjan, मेरी आवाज आ रही है गुंजन? हेलो, Gunjan, can you hear me? You have to unmute yourself. You have to unmute.
I,
हाँ, फोन में स्पीकर को ऑफ कर दो, फोन में केवल फोटो रहेगा.
कर दिया मैम, फोन में ऑफ
हाँ,
किया है फिर भी हो रहा है इको.
इको हो रहा है.
हम्म.
अच्छा, but here sound is very clear. Only backside light is very high, so your face it is reflecting.
But more than that, this sound is disturbing. This echo one. I think then it will not be clear, right?
Okay, no problem. So first slide, first we will take the photo, and then after that we can.
Okay. Okay.
Asha ma'am, take the photo.
Yes, ma'am. I took the screenshot. Can you just adjust your camera, ma'am? Your face is not visible, complete face.
Is it okay
No, ma'am.
now?
No, your face is not visible.
Oh, is it still? But
Yeah,
for me, it
yeah.
is showing.
हाँ, now it's okay. मतलब ऊपर से कट रहा है, थोड़ा नीचे करना है कैमरा, ऊपर यहाँ तक
अच्छा,
हाफ, थोड़ा नीचे आना, हाँ, या थोड़ा पीछे जाओ, हाँ ठीक है, अब ठीक है, अब ठीक, इट्स ओके नाउ।
Dr. Divya Vadvani, is it your system, ma'am, Gunjan ma'am? Dr. Divya Vadvani, somebody shared the screen. Is it yours, ma'am?
no. Which one? I can't see.
नो नो,
I have still not shared anything. I have
आशा
to.
मैडम,
Okay.
डॉक्टर
Ye-
दिव्या वाधवानी, यू प्लीज टेल टू don't share the screen or else you remove from the meeting.
Okay. Okay, ma'am.
Tell Chanappa because
Okay.
it will disturb.
So can I
Uh,
know, is it okay with photo? So I can switch off the
Photo is
mobile
okay.
thing then.
Photo is
yeah.
okay. All
Okay.
right.
Yes.
Thank you. So, and sorry for this that my camera is
No
not
issue.
working.
Issue. You shared the first slide
Yes, ma'am. Yes, ma'am. Yes, ma'am.
and Asha, please you inform to
Yes, ma'am.
Chanappa
Yeah, yeah. I'm calling.
and officially now you can start. Asha madam, officially you introduced the speaker. We can't hear you anything. Asha madam,
Yes, ma'am. Starting.
yeah, and you have to mute all the others.
Yeah. Yeah. Good afternoon, one and all. It is with great pleasure and honor that I stand before you today to extend a warm welcome to Dr. Gunjan Thakur to our faculty development program. We are privileged to have amongst us an individual whose dedication to education and depth of experience truly set him apart. With over 13.5 years of teaching experience, Dr. Gunjan has not only imparted knowledge but also inspired countless students on her academic journey. Their expertise spans a multitude of subjects, including embedded systems, Industry 4.0, advanced professors, advanced processors, RISC with SoC, and more. This breadth of knowledge is complemented by a hands on approach to teaching, where they have guided students through project work, facilitated practical assessments, and even led industrial visits, enriching the learning experience beyond the confinedness of the classroom. From her role as an assistant professor at Pandit Deen Dayal Energy University to her tenure as a digital design engineer at Neurospaces Private Limited, Dr. Gunjan has demonstrated a passion for both academia and industry. Her research contribution, particularly in the realm of digital circuits for system on chip devices, stand as a testament to her intellectual curiosity and scholarly pursuits. As we gather here for this faculty development program, let us seize the opportunity to learn from the wealth of knowledge and experience that our distinguished guest brings to the table. May this program serve as a platform for collaboration, growth, and exchange of ideas that further enrich our collective journey in academia. Please join me in extending a warm welcome to Dr. Gunjan Thakur, whose presence today elevates our program to new heights. Thank you. Over to you, ma'am.
Thank you, ma'am. Thanks a lot. So before I start my talk, I really thanks the organization and Asha ma'am for giving such a nice introduction for me.
Thank you. Thank you,
And
ma'am.
with this, I would like to just, as all of you, I think, can see my uh, slide I have shared. So you can see the title. It is Optimized Digital Cross Connect Switch for SoC. And we all know that from past few days, we all are here for this FDP, and the title of FDP is more towards Advanced Quantum Computing and Sensor Technology. So my idea here is to why to take this topic is that we all know that SoC is nothing but system on chip. So my idea here is to demonstrate this topic so that finally we can take it up as a research work or challenge to implement it through quantum computing. So let's start with this first. So we will get exactly that how this topic is related to our advanced quantum computing. And this is my overview, or you can say the outline. So basically, initially, for few slides, I will give you some idea of this cross connect switch and this switching network. And more than theory here, I would like to focus that why I have taken this switching network, because more than theory, I have focused here on the application area. So when we will start with the real presentation, you will come across that this particular thing, this cross connect switch, is really some miracle type of thing, because it has huge number of applications. And in this FDP, as we know that we all are from industry or academia background, so we all are familiar that we all are interested in something which has n number of applications. So if something is very good and application is limited, so we don't get attracted towards that thing. So because of that reason, I have particularly selected this, because this switching network and switching is something which has a vast area, from a small switching network to a huge, you can say, communication to an aircraft also. So because of that, I have taken this switching network, and towards the end of this presentation, I have kept, you can see in this slide, two topics related to implementation of this cross connect switch with quantum computing. For that only we all are here to explore this area, and the purpose of this FDP is towards that. And you can see towards the end, I have kept the challenges with quantum cross connect. So the last two topics basically for all of us can give us some opportunity to carry forward our research in these two area, because this carries lot of application area. So before I say a few more words, let's start with the thing. So I know we all are quite familiar, but just because switching sometimes there can be many definitions. So here, for what switching I am talking about, for that only I have kept this thing, that switching is nothing but a circuit between two devices. You can say something called sender and something called receiver. So a switching network, the task of a switching network is to establish some kind of connection between two devices. So switching plays actually a very crucial role in that, because our speed, our efficiency, our power dissipation, whatever parameters we are struggling to design any circuit actually depends on the performance of our switching circuit. So we all know that we do lot of algorithms, and we do lot of analysis to minimize and optimize as much as possible our switching network. So that's why even this topic has been selected. So again, the switching network can be of many type, but the most common switching network which is used nowadays in any SoC, that is system on chip or any network on chip, is the digital cross connect switch. So a digital cross connect switch is nothing but you can see this diagram. So this is a very general block diagram. Intentionally, I have kept a general block diagram, and then based on our application, we can make this diagram specific. But in general, if I have to say, so a digital cross connect switch or a digital cross connect system basically consists of these blocks. So where basically the DCS crossbar where I have written, that is the area, and the arbiter which I am showing in this diagram, it is actually not outside this diagram. It is basically the logic that is giving the signals to this crossbar switch, and through that it can connect different ports at the input end to different ports at the output end. So basically, the arbiter that all of you can see on this board, the design of this arbiter decides the overall performance of this crossbar switch. So whatever algorithms, whatever hardware, from the point of hardware point of view, whatever optimization we want to do, everything depends on this arbiter. And this particular talk will also focus more on that when we talk about different algorithms, whether it is simple, whether it is through AI algorithms. Nowadays, we all know that artificial intelligence is required everywhere, and because of good accuracy and prediction, we all are trying to go for through AI algorithms and all. We are trying to implement the things. But my concern here is because of this keeping this switching circuit, my concern here is that is it possible for us that whatever algorithms we are proposing, is it possible that do we have the sufficient hardware to implement that? So that is a question which comes here, and because of that, we can relate this to quantum computing. Because when we talk about separate algorithms, getting the efficiency, getting the result of algorithm is fine, but do we have the sufficient infrastructure, the sufficient hardware to support these algorithms? Because on paper, getting the simulation result is fine, but until unless we are not able to implement, then we will not be able to use it with respect to application. So that is the main target of this particular talk, that we have these switches which has lot of applications, but can we go ahead with the proper implementation, and can we go ahead with the quantum computing implementation of these hardware? So moving ahead, so like initially I said that major, the purpose of selecting this topic or a cross connect switch is what I thought that it is an FDP, and we all are here from different colleges and industries and domains. So whatever you can see on the board, I'm quite sure that somewhere or here or there, wherever we are doing research, our application area comes in these domain. So if we can do something towards switching network, we can target all these applications. And these are very common applications because you can see when I write data centers, so data centers, you can see the huge area of the data centers. A data center can be just between two rooms in a college, if you see that area. So then it can be implemented only through LAN, or a data center can be somewhere at the ground and some center which is in your aircraft, which is controlling your aircraft at the airport. So you can see the range of these data centers. So overall, by seeing all these applications, you can just realize that if we can do some work further for implementing these cross connect switches through our advanced quantum computing technique, so definitely it can give a very great advantage. So with respect to that, I'll move ahead, and here I would like to give actually this through this slide, I would like to highlight that what work actually here I have created, and what are the things we have right now. As per my knowledge, we can have something more also, but as per my knowledge, what are the things possible to go ahead with switching towards the quantum computing? So as I've already told you, that switching is nothing but some kind of rules or protocols which gives some connection between two devices. So you can see again, I'm going to the previous slide. So this is just a sample that we can have these four protocols or algorithms, you can say, but we all know that it is an unlimited thing. We can have our own design protocol. We can have some protocol where we can implement some AI prediction. These are just the basic, because we all know that whatever protocol we design, the basis of those protocols are these. Either we go for the round robin technique or request acknowledgement or priority or bulk data. So these are not the name of the protocol, or these are not designed by our team. This is like we have kept here this to show that whatever protocol we design to implement through our quantum computing, normally it is based on these four. So I've kept here, and as because of time constraint also, in these slides, we have worked on all. We have done the simulation for all, and currently we are working. Currently, that work is in that stage that can we implement it successfully, entire all the algorithms through quantum computing, and then we can perform a comparison. So because of time constraint, in this presentation, I have not kept all. I have kept only two as a sample. So through that, we can go ahead with others also. So, like one of them is, as I already mentioned, round robin. So, this is one kind of implementation because we know that right now quantum computing is in its initial stage, and towards the hardware implementation, definitely we will have challenges. So, towards the end, I have also kept the challenges in my slide, and we know that whenever we are going for some research work, these are the predicted challenges. But when we will do and we will go for real time implementation, we may face some other challenges also. So for that reason, here I am showing you a very simple circuit where we have, let's say, only four transmitters and we have three receivers, and it is not always in our hand that the ratio of the transmitter and receiver is equal. So for that reason, I have taken an asymmetric concept, and we can easily see that we have four transmitters, and through the table which I have kept on right hand side is something called time division multiplexing. So we all are familiar with that concept. So even if you are not familiar, it's fine because just by seeing the diagram, we can understand. So basically, in this communication, each transmitter has given different slot, and just to make it simple, it's not compulsory, but just to make it simple or just to keep it simple, we have designed in such a way that when A got the chance to transmit the data, so one by one it is sending to all three. So this is one way, and then further we have done the. We all know that whatever we design, until unless we don't simulate, we cannot justify the work. So we have done the simulation and we got the results what is expected. So expected means what is matching with this table. So with that we can say that theoretically this particular concept or this particular architecture for the round robin switching will work if we will go ahead with this technology. Similarly, as I said, that the next very crucial, and I'll just go back to again to this slide because I said because of time constraint, because there are a few more things I want to discuss. So because of that, request and acknowledge and priority based switching, intentionally I have not kept right now in the slides, but we have worked for this also, similar kind of one architecture we created and then we have implemented. So if any one of us are interested, instead of round robin, it is our choice. Based on the application, we can go for request and acknowledge implementation also through our quantum computing and priority based switching also we can take. So I have taken after round robin the concept of bulk data transfer. So this is highly used in many applications because we know that in today's world, we all are always almost every time connected with internet. Okay, and it's not connected with internet means we are simply chatting. Today we all are doing multitask. We have kept something on download and we are talking also. We have kept on our speakers on. At the same time, we are reading some data. We are listening music and we are watching some movies. So many things are going on. So because of for that concept, we have also designed this circuit, that bulk data transfer. So sometimes it happens that we all familiar that these all datas have different size. So if it is a video, if it is some animation, so definitely those datas comes under bulk size. So in this design, we are giving an option that if we have a bulk data, so in order to facilitate the faster transmission, we can provide a separate channel for bulk data, so that the normal channel don't accommodate when you have a bulk data. And obviously, we all can see, you all can easily see that on left hand side it is just a proposed block diagram, but the actual circuit is on the right hand side. So again, this research work is just in its initial stage. So I have kept a very simple circuit by keeping only four transmitter and three receivers. Further, if we get success, we can definitely expand this with the number of transmitter and receivers. But that is definitely one of the challenge with quantum computing because scalability is still under research, that how we can go with the scalability. But that I will not reveal right now much because that I have kept in my last two slides. So there we will have a discussion. So here I just want to point out that if we see in a broad way, just on the top level, I know there are some hidden components, but okay, if we see on the top level, so we all can easily see that basically to implement this, we need basically only two circuits. So one is the demultiplexer and one is the counter. So idea here is that if we start with these simple circuits, to implement in quantum with the quantum computing. So even what we can do is that right now we are working with the same idea, that what we can do, that let's take one component, 1 is to 2 demux, let's take one component of byte counter, or we can give to one group this and another group that one. So then we can design and then we can combine the result and we can see the cumulative effect. So this is also one of the switching circuit which has a huge number of applications. So if we can implement this also through our quantum computing, definitely we are going to save, we are going to have an efficient design. So as I said earlier, that definitely if we design something, simulation is must. So this particular graph gives the simulation result, and whatever we have designed here, we have verified. So it is working exactly what is our design with our design. Okay. So with that, with that, I have already said. And again, sorry, going back to my previous slide. And with this, all four, which are the basics for any communication between two devices, gets accomplished. So now this is the circuit. So these two we have already implemented actually, and we got the results also, even in the hardware. Fine. So currently, exactly, we are working on this one, which is quite a novel idea actually. And we are currently working on this. And if we get implementation of this one with the real hardware, so that is definitely going to have some count in the real world for many applications, because this particular idea, this particular circuit is nothing but something called, sorry for not writing the full form of exactly this IS. So this IS is something an intelligent switching based on data rate. So as I already said, that round robin, bulk data transfer, these are defined. These are already defined. We are just using them to implement something. But this is something we have proposed by ourselves, that can we have a circuit where switching is done on the intelligent, some intelligent decision can be taken. So here intelligent means based on the frequency and based on the time. Can we segregate our data in order to just the overall idea and target is nothing but just to boost the operation, just to make it faster. So that if your channel is occupied by some data which is not that much critical, so better what we can do, that we can have two channels. But at the initial level, we need to recognize that which is your voice data and which is your normal data other than voice, that is your audio, video, text. So basically, this circuit gives an idea that initially, as you can see, I have mentioned here that something called input data is coming, and then that input data is nothing but a combination of voice and data. Yeah, we can see that I have just written data word, and we all are familiar. This data word writing is so simple, but it's not so simple because the data is nothing but video, audio, text, some animation. There are so many things, and all those things need a lot of processing with respect to time also and with respect to memory also. So because of that reason only, we have proposed that can we have something, a hardware-based switch which can basically segregate these two, so that we can little bit enhance our performance. As I already said, if you can see here, so again, counter is a repetition. If I compare with my previous circuit, byte counter, and here pulse counter, some changes internally would be there that we can do, but ultimately it is a counter. So if we can get a hardware, means a counter implemented with a quantum computing and compared with the existing one, implementation is a different thing, but what is our target is, if we are going for something, some new technology or something new, we must get some advantage compared to what is existing. So what is existing with our normal counter, that is with our CMOS technology. So do we have, can we implement a counter with a quantum computing which can give us a better performance? So if we get that, and if we replace that with our CMOS counter, then definitely this circuit has huge number of applications, and this will help us in many domains to make our system quite efficient and faster. And similarly, we have some comparators, demarks. So obviously, when we have moved from that circuit to this circuit, it has become a little bit complex because obviously there I have considered only one scenario that you have a bulk data. Here I have considered the entire domain, that how we all are connected together to internet. So whenever we are connected, we have both voice and data. In the similar this one, okay, before I go to the next one, definitely I have kept just for the sake of proof that yes, we have also implemented. So it's not only the top level block diagram. So this is the simulation based on the frequency. But this is the main thing which I want to highlight. I told here itself that the purpose of my intelligent switch, of this intelligent switch, is to basically segregate the two things, because we all know that voice is nothing but some low frequency components, and compared to voice, I cannot say that all the data is high frequency, but compared to voice, they are some high frequency components. So initially, when first time we have done the segregation with frequency, and next time, let's say we go, now at the next stage, I got the data. Which is based on the call. Again, further, this particular stage says that again, to improve the performance, we can further divide our the voice call into 2 3 domains based on the call duration. Again, for simplicity, I have considered here only three, that is short call, medium call, long call. But it depends on the designer to make it less or make it more. Means we can increase the capacity, the range, how it is defined, or we can make it less also. Because you can see, like, as per our design, we have kept 1 to 60 seconds for short call, 60 to 180 for medium. So we all know that these all are flexible, scalable. So as per our choice, we can go ahead with the other things, means other parameters. We can increase or decrease this particular range so that we can cover the entire area. So my target here is to highlight again. See, we all can see that again that counter has come. So basically, the thing is, if we can design these counter hardwares through our quantum computing, so you can see from the beginning, we have seen its application in many areas. So by designing only a single component, that's what I want to highlight here. That if by designing just a single component also, we are contributing a lot to complete circuit. So with that also we can enhance the performance. So this is based on the call duration. Here IS again means intelligent switching also. So this particular circuit is actually the continuation of the previous one. So, and again in the next slide, then I have kept the simulation result. And here I want to give one more information, that currently also one of our students in MTech in Masters, they are doing work on this, and they have got almost very good results with respect to up to Mod 6 and Mod 3 counter. So they are facing some challenges that I would like to discuss, so that if somebody can get the solution for that later, through personal email or something, we can share our ideas. So like I said earlier also, that last two slides I have kept the challenges, and which my students are facing, and which if anybody takes up this work might face, as per my information, as per my work, what I have collected, the points I have kept here. So these are the things. So this is up to yeah, this I've already discussed. So I have kept that, if we, because right now my we are working on this intelligent switching. So the basically we are working on intelligent switching or intelligent cross connect switch implementation through quantum computing. So how I have taken this work as okay, analysis of quantum computing, we have kept it at one side, and the complete this one, when we are doing the analysis of this and the circuit design of this, we have not kept any like suppose I'm designing this circuit, so we have not kept any particular hardware domain in our mind, because the first target, we know that when we go for design, we have to design the circuit and we have to simulate. So that's what we have done. And after getting the successful result, we have two options to go for implementation, because as I already told you, my domain is more towards the hardware implementation of the concepts. So when our team design any, we work on any particular algorithm or any particular design, so we keep two things in our mind. One is application, because if it is more in application, definitely it is going to be useful, and later we can file for some patent or something. And second thing is, when we design an algorithm, initially we keep the number of users and all very less intentionally, because in simulation we all know that you keep on increasing the number of users. You will definitely, because if you get the result for two users, it is very simple through the software to just increase the number of users and get the result, because the main thing is to get the result for one user. You can do. I'm not saying very easy, but yes, we can do. But when you go for the hardware implementation, scalability is a very big issue. So, and especially when you are jumping to completely new technology, which is still at its infant stage. So definitely we have to see what are the resources available and how we can do. So intentionally in this design, we have kept number of users as our target, only one or two, three transmitters. Because once we get the implementation of that, we can definitely go for the scalability. So that is the idea here, and all that I have kept here, the advantages of this complete. Yes, and in this design we have explained three levels. That's what I was explaining here, the second point, that it's not restricted to three level. It's not restricted to four transmitters. So even how we can do that, one of our group, like how they are doing, somebody can design mod 6, all counter call somebody can take, and somebody can take all mux, and then we can combine also. So basically, as I am towards the hardware implementation side, so implementing through hardware is my main target, and whatever circuits we have designed or whatever algorithm we are talking about, so we are targeting the implementation also. Now, coming to our thing, so this is the complete circuit. This is the complete circuit where, because of time constant, actually we have designed we all can see on right hand side. There are so many protocols and algorithms I have kept here, but I cannot keep the explanation and circuit and simulation for all, because uh, in the limited time I could have kept only this much. So basically, this is the complete SoC. This is a complete SoC that I was talking about initially. So right now, how we have planned here is that we are doing module wise implementation of all, and and then combining all the modules, and then we have two options. Like right now, we have done the complete CMOS implementation of all. So that is one part. Moving towards the advanced quantum computing, or let's say the quantum computing implementation of all. So that is the main thing I want to highlight here. That with this, we can take one by one particular module, and we can go with the quantum implementation of that, and then we can analyze the result, that how if the same switching network is with CMOS, and if the same switching network, we can go with the quantum computing effect. So with respect to hardware, how much difference is that? And if we can do some further improvement in the design of these circuits, with which we can get the further result, so definitely that will work. So basically, this complete SoC, you can see the right hand side, all the protocols definitely gives the idea that we can cover through this many application areas, because wherever we go, at least one of them or two of them or three of them we are using here. So that's why this architecture name is given as okay, fine. Innovative is little bit incomplete, because once it is completely implemented with quantum, then we can say that it is complete innovative thing. So that innovative word is actually kept with respect to the future implementation, that if we get the success to implement all this through quantum, then we can do. So this is all about till the circuit, the architecture, the application, and the domain through which we can go ahead. Then next, so this is the area we are currently working on this. That fine, that are all already implemented, and till then it was just the idea that can we do through the quantum computing. And when we did some work, some information, some research, so this question comes in front of us, that can a cross connect switch be, sorry for the spelling mistake, can be implemented with quantum computing? So that's the question, and we are currently working on this. So what we found that we all know that this is as a concept that quantum bits can exist in superposition states and which can represent multiple states simultaneously. So that allows for parallel processing. So this is a feature because we know because this cross connect switching is nothing but like a matrix. So at each matrix, I have a point. So, and all the matrix points, joint points of rows and columns, they work with parallel processing. So if we can implement those particular joints and points with quantum computing, so it will result in a parallel processing. Another very important area which I want to highlight is the quantum algorithms. So like I already said, just 1 minute for this one. When I was explaining this, so I have explained that few of my students are currently working on the design of this particular thing, and later they will try to make it scalable also. So that exactly what they are working is they're trying to design the same algorithm. Which we have done is through the quantum algorithms, like what I'm highlighting here. So can we develop to optimize because what is our purpose if we're moving from one technology to another? So definitely the routing and switching process should be optimal. Currently, we are working on this, and this is a very upcoming area. Where we all can contribute, we all can work quantum algorithms. So could be so my here suggestion and what I am working is many have done work on quantum algorithm. So if we can, let's take one by one and try to start implementing. If we start moving towards the implementation part, then we will get the real efficiency. Because, like I already said, implementing, generalizing some algorithm, comparing it with some existing algorithm, fine, definitely. And obviously, they have given us good results with lot of proofs and the research and paperwork. And that's why we have kept this topic that advanced quantum computing in our FDP. So because we all are familiar that they are giving us a lot of advantages. But the question is, can we implement these quantum algorithms through hardware? Are they scalable? That is a big question. Can we design some quantum algorithm with cross connect switch? So the two groups which I am working or we are working is basically hitting this area, quantum algorithms. So we are trying to find out some options or can we write some algorithms through this approach so that we can have a better routing and switching process. And then the third option also, we have not worked on. This is just an idea which we can carry forward next. That is quantum gates. So quantum gates also, if you can see, I have written on the slide that by designing appropriate quantum gate sequences, it is possible to perform necessary logic and routing operations. So as we are familiar that sequence arrangement and sequence, the flow of the network, the flow of communication plays a crucial role in the overall performance of a quantum computing. So because as it is with respect to the hardware, so if by placing some circuit, some gate sequences, if we can interchange those, so that is also one area that we can just take the circuit and we can interchange the blocks. So we can interchange the gate sequences, and then we can find out the result that can we get some benefit here in with respect to the overall performance. So the idea of putting this particular slide is, as I have mentioned here, only three. So it's not limited to three because what I found connected to the cross connect switch where I have worked, I have tried to connect the cross connect switch with the latest advanced quantum computing implementation. And as I already mentioned, superposition, first point, and quantum gates is just an idea in the pipeline where people have done work, but it is still going on. But our team has already started work on quantum algorithms, and maybe if we are successful soon through these algorithms, the same round robin and all what we have discussed right now, that was the basic. And with this, then we can implement the same algorithm with quantum. Further, we can carry forward that for the real hardware implementation. And yeah, so like if you can recall in between, I said when we go for the hardware implementation. So these three, we found these as challenges. So this I'm projecting in front of everyone. If somebody is also working in terms of the hardware implementation and quantum computing, the hardware implementation. So we found these challenges. It is again not limited. These challenges I have kept not the general. when we go for implementation, we will get it. It's not a general thing. These are these three challenges which our team is currently facing. So, and it is open for discussion. If anybody wants, later we can discuss also. So, one is called physical implementation, and especially scalability. Okay, because scalability, I said, like whatever diagrams you have also seen, where there we have proposed only two or three. So when it comes to simulation, we will increase, but it is just in its initial stage, this quantum computing. So the big question comes with scalability, because when I'm saying that this cross connect switch has a lot of applications and mobile network and this, that, so if we are not able to connect with number of users, more number of users at the same time, and it might be possible that when we are connecting more number of users, our performance is degrading. So then also there is no point. So scalability is one of the challenges, and obviously error correction. Error correction is also one very big challenge is there, because we know that for that also we have to design a complete thing, because just sending and receiving data doesn't matter. You have to keep on checking the error. We have to, so again, those things need some particular algorithms and all. So if I'm talking about a complete SoC, if I'm talking about a complete SoC, so it should be a complete implementation. That's why I've put the challenge, the physical implementation first. It cannot be just the counter with quantum computing and the other circuits with CMOS. So it is a complete SoC should be designed with quantum. So we are just at the initial stage of that. So right now we are working with module-based design. So let's take one module and implement it. And in the next stage, then we will combine all the modules and we will try to implement this complete circuits, which you can see. So these are the modules that I was saying, that module-based implementation. And then final SoC, this one, and then we will see the interfacing between all. So these are the challenges we have currently faced, and we are working on this. And we got some ideas also. So this is the thing. So to summarize this, I would like to give you principle of quantum computing. You can see here offer various possibilities for implementing cross connect switches with some unique advantages. Practical implementation faces that this is the point. If we all can see that this is the main thing which we are working on, this that practical implementation faces substantial technical hurdles that we have to overcome to further research and development. And currently, to highlight that scalability is one of them, where this area we are working, and we are hoping that we will come up with some good results for that. So that is all about this one. And as I already said, it's not limited to two or three algorithms. We all are familiar. There are a number of algorithms. We can take others also. So thanks to all of you and for listening. And I'm open for any discussion, any question, any suggestion also. So we can go ahead with that.
Thank you, Gunjan, for giving the elaborate discussion on cross connect. So, any question from the participant side? Anyone who is from VLSI domain, they can get benefit. If not, only I have one question, Gunjan.
Yes, ma'am.
Yeah, actually, I was thinking that uh, how you can do in the quantum. So, in your
Mm-hmm.
knowledge, someone is SoC design, someone is doing by
Mm-hmm.
using the quantum algorithm, because if any interface you will do with the quantum, then the paper quality will be
Mm-hmm.
very high.
Mm-hmm.
Yeah, so I was wondering that if anyone is there in your domain, if you know someone who, or else how, what is your opinion about this?
Yes, ma'am, sure. Because even like I told you, ma'am, if you can see this slide, like 2 3 students are working on this. So currently they have reached the stage where they have implemented these counters in their CMOS and this complete circuit. Okay, so
Okay.
right now these students themselves, they are working on the study of this hardware implementation of quantum computing. So once they will finish up that, so with small small components they can start implementing, because we have some tools available, so that they are exploring. So once they can do, but before that the thing is some changes in design, some interchange of the gates sequences, that they need to do some timing analysis and all, exactly the same thing what they have done for CMOS. They cannot just copy paste, so that area they have to work.
And second thing, in your work you have done in
Hmm.
Verilog. Can you import that to the cadence in VLSI, and you can calculate the full
Yes, yes,
area?
yes, yes. Yes, ma'am. Even nowadays, this Vivado tool also, this the higher version of Vivado tool also gives a complete analysis with area, time, everything. A new
So is
version
there
and
any
everything has come.
possibility to import directly from the
Yes,
Verilog to the
yes,
cadence?
yes, 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 ma'am. Yes, yes, it is
Then
there.
very good
Not.
actually. Your all paper you can convert into another paper by taking that
Yes.
into the. Is it possible?
Yeah, we can try, ma'am. Sure, we
Okay,
can
very
definitely
nice.
try.
Good. So this is very good learning from you that Verilog already, if we have the code, directly we can import in the cadence, and we can calculate the area
Yes,
and
ma'am. Yes, ma'am.
power. These two
Yes, ma'am.
two
And then
things
we can compare with that with the quantum
we can
computing
compare.
implementation. Yeah. Yes, ma'am. Yes, ma'am.
Okay, it's good. Okay, from participant, any question? No, maybe they are not from the VLSI domain, because
Yeah,
most
might
of the
be. Yeah.
talk are
Yeah.
related to photonics and quantum.
Yes, yes. Okay.
So thank you. And
Thank you, ma'am.
Asha madam,
Thank you.
you are there?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Thank you so much.
Okay,
Thank you
so
so much, everyone.
thank you,
Okay.
Gunjan.
Yeah.
I will tell everyone to switch on the camera so that we will have a group photo, and then Asha will end the session formally. Gunjan, can you
Yes.
on your camera also?
Yes, ma'am. I am also doing, ma'am. Just give me a second.
Just for the sake of taking photo. So you unshare
Yeah.
your slide. You unshare your
Yeah,
slide,
ma'am. Yes, ma'am. 1 second. I'll just do that.
because I am planning this. Gaurav sir told that if everything is good, then I will put in the Gyan portal. So if we are eligible to put, we will put. So I want the photos. Very few are there. Uh, main speaker, your photo is not there.
Am I visible, ma'am? No, no. Mm, 1 second, ma'am. I think now it will come. Now it,
Okay, because you have to join from the mobile, na?
yeah. So is it okay, ma'am? Visible?
No, that time it was visible. Asa ma'am,
Yeah.
kindly take
1 second.
photograph,
Yes, ma'am. Taking screenshots.
because many we have done, but we have not taken photo, group photo.
Yes. Yes, ma'am.
We can't post actually. Each
Uh,
15 they
Ma'am,
told.
Gunjan, ma'am, you're not visible.
Yeah, I know.
Yeah,
I know.
yes,
I
ma'am.
can see that I'm not visible, but I have connected through phone and I
Just
can see, but I don't know.
phone, you just show your face, camera on, click the camera. That's all.
I don't know who it is showing. Uh, Today we have some issue in our college related to. I think now it is. Is it okay?
No.
No, ma'am. Okay.
I think in mobile phone, na mobile phone in our mobile phone, easily we are going to the team.
Yeah, yeah, I have switched on to mobile phone.
Some issue will be there in your phone only.
Hmm.
No issue. So how many
Yeah.
photographs are there? Asha madam, can you
Yes, ma'am.
shift and take the photograph? Because in one single screen, four will come.
Okay. I think many haven't turned on the camera.
Oh,
Yeah,
many people have
I can.
not turned on the camera. I will
No, no.
request all of you, please turn on the camera. Okay, and in chat box, please give the feedback form. It
It's
should given
shared,
in
ma'am.
afternoon session,
It is
not in
shared.
morning. Okay. Okay. Asha, you have taken the photograph, snapshot.
Yes, ma'am. Yes, ma'am.
Okay. Then formal way you can end the session. Yes, Asha?
Yes, ma'am. Starting.
Yeah.
Uh, On behalf of the Oxford College of Engineering, I would like to extend our sincere thanks to Dr. Gunjan Thakur for graciously accepting our invitation and delivering an outstanding session on the subject of optimized digital cross-connect switch for SoC. During her presentation, she elaborated on utilization of cross-connect switch for quantum computing and highlighted the challenges it poses, which remain an ongoing endeavor. Also, I would like to extend appreciation to all the attendees for their participation in the FDP session. We hope you enjoy a fulfilling and enriching learning experience. Thank you all. Thank you, everyone.
Thank you. Thank you, ma'am. Thanks a lot.
Thank you, Gunjan. Thank you so much.
Thank you, ma'am. Thanks a lot, ma'am. Thanks a lot
Thanks
for giving this
for
opportunity.
agreeing to give the talk in such a short
No,
notice.
ma'am. I should say thanks to for giving me this opportunity to speak in front of such big personalities. I'm really thankful.
Your work is very good, very nice.
Thank you, ma'am. Thank you,
You
ma'am.
keep progressing in this area.
Thank you, ma'am. Thanks a lot.
Thank you. Thank you.
Thank you.